Without further ado, I would like to request our principal, sir, Dr. Tirthankar Datta, to open this webinar with a welcome note. Sir, if you may.
Hello, am I audible?
Yes, sir, you're audible.
Very good morning to everybody. Professor Chakrabarti, how are you?
Yes, I am fine. I am fine, Professor Datta. I'm fine.
Yeah, okay. Just 1 second. Yeah, Professor Amlan Chakrabarti, Professor and Director, A.K. Chaudhary School of Information Technology, University of Calcutta. Professor P.L.E. Chatterjee, Head of the Department, Computer Science. Other distinguished professors of Computer Science Department. Team GNX, my dear students, ladies and gentlemen. We have gathered here in this August gathering to welcome all the participants of the program called Deep Networks for Computer Vision. It is a very relevant topic of today's context, and believe me, in this new normal and this forthcoming Industry 4.0, these areas are the most upcoming areas. And on the behalf of Netaji Subhash Engineering College, I welcome Professor Chakrabarti for sparing his time from his busy schedule for our students. And I'm very glad that my students will be immensely benefited from this topic, from his speech. Professor Chakrabarti is a full professor in the A.K. Chaudhary School of Information Technology at University of Calcutta. He is an MTech from University of Calcutta and did his doctoral research at ISI, Kolkata. He was a postdoctoral fellow at the School of Engineering, Princeton University, USA during 2011-12. He is the recipient of prestigious DST Boys Cast Fellowship Award in Engineering Science 2011, Indian National Science Academy INSA, Visiting Faculty Fellowship 2014, JSPS Invitation Research Award 2016, and so on. He has received multiple project grants in the areas of security in cyber physical systems, embedded system design, VLSI design, quantum computing, computer vision and data science from numerous national and international agencies like DST, DRDO, UJC, Ministry of Social Empowerment, Tata Consultancy Services, Intel India, and so on. He has published 150 research papers in referred journals and conferences. He is an associate editor in the Elsevier Journal of Computers and Electrical Engineering and guest editor of Springer Journal of Applied Sciences. He is a senior member of IEEE and ACM, distinguished visitor of IEEE Computer Society, distinguished speaker of ACM, secretary of IEEE CEDA India chapter, vice president of Data Science Society, and life member of CSI India. His areas of research interest are machine learning, computer vision, embedded system design, VLSI design, and quantum computing. So, my dear students, you are fortunate enough that we have today, we got Professor Chakrabarti, and I do believe that you people will be immensely benefited from his speech. Thank you. Thank you very much. Welcome once again.
Thank you, sir,
Thank
for
you, Professor
introducing
Dotto,
our guests.
for sparing your time and for introducing me.
Thank you.
And without further ado, the guest of this time, Dr. Amlan Chakrabarti. Sir, if you may.
So thanks, Professor Dotto, the principal of Netaji Subhash Engineering College. Thanks to all the faculty members of the Department of Computer Science and this college for organizing this lecture, and thanks to the students group, right, who have taken the initiative and who have communicated me, I think, uh, maybe 2 weeks or 3 weeks ago, and made this particular program and requested all the details from mine so that this lecture can be well done. So, so it's good that the college and the Department of Computer Science and the students have taken initiative to get into the topics related to machine learning and deep learning, which are really very exciting domain, not only in the domain of computer science, in the domain of engineering, in the domain of science, in the domain of social science. A lot of activities are going on, and I am involved with this particular domain for the last 6 years. When I started my project on computer diagnosis with funding from Ministry of HRD, uh, it was a Center of Excellence project on the TechU2 program, and I was the principal investigator of a project, and from that on, and from then onwards, I just went on working in different projects involving machine learning and computer vision, and also the various other domains of machine learning. So my today's lecture, okay, what I will uh, try to convey to all of you is on a particular is not on a specific topic of or a specific application domain of machine learning for computer vision. What I try to present is some of the very fundamentals or some of the very baseline concepts, right, of deep learning, which can give you a good avenue to work with multiple computer vision projects, right? And I will uh, try to explain the very important fundamentals, and why I will be doing this, because I find many of the times the students in the domain of deep learning and machine learning, the students just try to work with the libraries and uh, just try to work with the built-in codes which are available in the various repositories like GitHub and Kaggle, and just try to uh, finish that job. So, what I want to tell here is that, see, we are engineers, or we are rather scientists or researchers, right? We are not persons who will just use these things, right? We will not be the users only. We will be the people who will be trying to address new scenarios, trying to propose new solutions, and try to propose new models, right? And when we try to propose these new models, what you need to know the underlying computational algorithms, or the underlying computational techniques, right? Which defines this deep networks, right? And what I will try to do in my today's talk is basically I will try to address those issues, and I wish that the students and the faculty members will connect with me in this particular lecture, and try to explore this domain in a in a much better way. So without wasting my time, I will be starting my lecture, and so I feel that I am audible, and my presentation is visible to all of you.
Yes, sir, it's visible and you're audible.
Okay, great.
Please go ahead.
Great. Okay. So it's deep networks for computer vision, and uh, so before going into the deep networks, as we know that the deep networks are which are used for deep learning is also is a subset of machine learning techniques. Uh, okay. So prior to going to the deep learning, I will just introduce you the concept of machine learning. So So machine learning was coined by the father of machine learning, Arthur Samuels, in 1959. So he told that the way we do the program, okay, way we develop the program, okay, for computing tasks, right? Okay, a process of program development will come, right, which will be very different, okay? Where we mean that, what it tried to mean is that the computer programs we develop, okay, they are basically based on certain assumptions of certain algorithmic path, right? We choose an algorithmic path, and then we try to generate a program out of that, and then try to fit the program in my machine, and the machine works, right? But those type of programs fails in many real-time scenarios because the algorithms there were some assumptions of the algorithms, and those assumptions are not valid, okay, in certain scenarios, and then your program fails miserably with time, right? So with time, as we know, the scenario changes. That means if you don't have adaptability in your program will fail. But what Arthur Samuels told, that it will be, so the way the machine learning models will work, it will be a sort of learning paradigm. So which means that the machines, okay, or the algorithms, right, they can always upgrade their knowledge, right? So the term learning means that you can always have an upgradation in your knowledge, and by that you take decision. So machine learning models are something like that. Okay, you try to look into the problem space and try to gather the knowledge, and try to enhance your program, right? Enhance your program without being just focusing on a particular algorithmic approach. The system will try to explore all possible approaches, or the best possible approach out of all possible approaches, and try to do an update in its logic, uh, okay, by going through various scenarios, and that makes the machine, which is a sort of uh, okay, that means knowledge-based machines or knowledge-based systems, which have a learning strategy, right? And that what predicted by Samuel. And on the same line, there was also a definition which came from Tom Michels, okay, 1997, who told that means as these machines, or as these systems, machine learning models has a learning curve, okay, or as a learning strategies, these machines will perform better through experience, right? And this is very true for a biological world also, right? In a biological world, we know that when a baby crawls in the floor, and slowly and steadily, okay, he or she becomes an adult, right? He gets a lot of experience, okay, either through his teacher or trainer, through his family members, through his friends. So he or she constantly gathers experience, and through that he or she knows that from crawling, how he or she can actually walk in a busy road. So this means that means our biological world, or our biological system, has a constant learning mechanism going on, and through the learning mechanism, we actually improve our performance, okay, okay, yeah, in our tasks. Now, if a machine can also do that, right? What it means that in a image recognition system, right? The recognition system might fail might fail in 10 iterations, but if you are doing 100 iterations of learning, or maybe 1,000 iterations of learning, right? Through experience, the machine will now perform very good, okay, compared to its performance when it just learned maybe with 10 iterations. So it speaks about a particular paradigm of computation, where computational tasks, okay, perform well, that means supersedes supersedes the performance from its previous experience, okay, than the experiences okay, it constantly goes through, and by the process makes its performance better and better, right? And then comes whether we can apply any problem of machine learning, or what are the main pillars on which this machine learning, okay, domain stands, right? what are the problems we can, or what are the things we need to have if we want to push machine learning in our computational strategy. So what do we need to first of all find out here whether there is some sort of pattern which exists in my domain, right? Whether it may be an object recognition problem, okay, it may be finding obstacles in a particular busy road. It may be detecting a particular voice pattern from your audio. Okay, it may be detecting a particular script from a given text, right? So all this tells that, hey, that means there is this problem inherently tells that you have to, okay, extract certain patterns, and from the patterns in your data, and from that you have to take a decision, right? Suppose you have the data of your company, financial data, and from that, whether you can extract certain patterns which tells that whether the company is going in a profit, whether the company is building up assets, whether the company is doing certain productions. So whether we can search these patterns, right? And these patterns are essentially based on some features which I will come later. So essentially the problem involves some sort of pattern analysis, right? And then obviously this problem cannot be defined in terms of a very mathematical formula, which means I cannot tell my outcome y is something 10 to the power of my xx and 20th power of my x1, okay, and this is a complex addition subtraction of the terms, and that generates my y. So I cannot have that type of computational stuff. So for example, I cannot tell you that provided I give you the data of the rainfall, provided I give you the area of the land, and provided I give you the properties of a particular plant, okay, can you find a mathematical model which tells that for that, what will be the growth rate of the plant for the next 5 months, right? Can you have any mathematical formula for that, right? You will tell that no, there is no mathematical formula exists between the rainfall, between the soil condition, between the plant type, and between the area of land. I cannot have any direct mathematical relationship by which we can just put the values and just evaluate what is the agricultural yield of a particular area. So this is the problem. So there are many problems which we cannot directly develop any mathematical argument, and then what we try to do, we try to generate a model which will either predict the outcome or will classify the outcome, and that brings the machine learning into play. Last but not the least, obviously, when we try to define the machine learning models, or we try to build the machine learning models, what we need to have the data, right? Without the data, so when I tell that you have to generate the agricultural yield of a particular piece of land, then what you need from me, that, okay, can you give me some example data, okay, where we have the data of the area, where we have the same crop which has been cultivated, and some of the soil parameters and some of the environmental parameters. So if you can give me the data of maybe 20 of such experiments, or maybe 30, maybe 50, maybe 100, maybe 500 of such experiments of such agricultural yield, then that means different parts of the country, different parts of the world, then probably I can build a model which correlates the soil parameter, the environmental parameter, in the area of the land, and the type of the crop. So what I am saying, just give an example. You might tell that, okay, sir is giving a very that means an example which doesn't work out in reality. So now, for your knowledge, the example what I gave, right, is actually worked out in reality. So this particular problem I got exposed from one of my student, okay, who is now a faculty in Nebraska Lincoln. Okay, she's one of our very best students in our MTech course. Okay, she's Shruti Das Chaudhuri. I think some of you might be knowing her. So actually they are doing this work. They are doing this work in Nebraska Lincoln, right? And what they're doing, they're trying to correlate the genotypic and phenotypic parameters. So phenotypic parameters are the structural components of your plant, and genotypic parameters are your gene information, right? And they're trying to do a lot of variations in terms of environmental effect, in terms of nutritional content of the particular soil, and try to find that which particular variety of the plant. Because if you tell that I want to grow mango, right, for a farmer, your farmer will give you what variety of mango you want to grow. There may be 20 varieties of mango you can grow. Then if a farmer is actually buying a piece of land and wants to grow the mango, farmer wants to know that which particular mango will give me the highest amount of yield, right? And maybe a variety X, which gives the highest variety of yield in Malda, may not be giving the highest variety of yield in Hooghly, may not be giving the highest variety of yield in a particular district in Karnataka, because they have different environmental variations. They have different type of soil quality variations. So this is a great amount of research, and then what you need to do, you cannot use mathematical components. What you need the data to generate. Either you generate the data in the lab, or you take the data from the existing experiments which has been reported in the various repositories, right? And that you can use to build your model. So these are the very these are the standpoints on which your machine learning algorithm works out. And that's why I was telling that, okay, that means so we require learning, and that's what's machine learning. So now this particular representation tells you that learning is so easy in the biological world, right? Learning is so easy in humans, right? A particular baby just out of his or her bed, okay, can just walk down in the room, avoiding obstacles. Okay, that means he or she maybe within maybe 6 months from his or her birth, right? Okay, he or she can, okay, it's identify the different type of sizes and shapes of the objects. Now, vis-a-vis when we try to do the learning in the computational world, right, we need to capture the data, right? Because the data will help us to learn, right? And then it becomes a very complex stuff, because the data what we capture in our machines are through various type of interfaces, right? It may be audio interface, it may be a video interface, it may be a human computer interface, right? And so different types of interfaces are there, and from that we capture the data, and that data we use for learning. So what I mean to say here is that means the learning in the biological world, which looks very seamless, okay, requires some type of effort to make the same learning in our computational world. So now let us straight into that. Means from the machine learning, we just go a bit into the computer vision, the main context of our today's discussion, because as we know that we can take a course on machine learning, which consists of different application areas. But let's focus on the today's discussion, which is basically the machine learning techniques for computer vision, and especially the deep learning techniques. So computer vision is something like that. You are trying to generate your vision sensing and vision processing, right, in your computational devices, right? And the devices may be very large, and the devices may be very small, like your smart devices, right? Accordingly, depending on the type of application, okay, you can spend days on analyzing the data of a space, okay, say a space image, right? What has happened in the space? You can take days to analyze that, right? Vis-a-vis when you try to do a recognition of a fingerprint, or recognition of a particular face, okay, through your smart devices, you need to do it within some milliseconds, right? So you see that depending on the application, depending on the type of application, you need to that means reorganize your resources, what you need to do, and maybe in some cases you need to reorganize the algorithms, okay, depending on whether you are running the algorithm in a very good resource device, or you're running the algorithm in a very resource constrained device. So basic paradigm, or if we try to compare what happens in the in case of humans, in case of human vision, vis-a-vis what happens in the case of machine vision, the analogy is something like this. This is a very simple analogy, and you can disagree with me, but I try to just give you try to explain you in a very simple form of what actually machine vision is. So machine vision means that you need to have some sort of cameras captures some sort of image or video capturing sensors, which are basically your cameras, your digital cameras, and then it goes to the processing engine, which actually interprets this particular image and tries to extract a lot of information out of that. And from that, it tries to generate a decision. Either the decision can be an object identification, or it may be counting the number of objects, or it may be identification of scene, right? Or it may be in the medical images, identification of the deformities, what is there in the particular image. So there may be various strategies and various ways we can look into the computer vision problem, and there are various applications for computer vision problem. So what do we try to look into the particular way the machine learning models works for computer vision. These are the this is a very simplistic view what I can place to all of you. So what it does is that it tries to capture the image features, right? And based on that, the model gets trained, right? And for that you require labels. So labels means that where you use the data which has already been classified. So training data means you already use a particular data which it's a sort of supervisory learning, which means that you already have the training data set. So training data set has the labels of all the images what you are using for training. So it tells that, hey, this is an image of a cat, this is an image of a dog, this is an image of a chimpanzee, and something like that. You can, you have the labels. So what your models tries, that means your models tries to find out what are the feature vector, what are the feature values which are for cat, what are the feature vectors which are for dog, and then on the base of the feature vectors, it dissociates or it separates the feature space, and in the feature space you can find that, okay, these are the region of class level 1, these are the region of class level 2, this is the region of class level 3, right? And once you can do that, it means that you have formed your classifier, through training. Once you have done your classifier, then actually comes the deployment. So the deployment, you actually just take any unknown image, and your classifier, if it is good, if it has a good accuracy, then it will correctly label the particular image what you have passed on to it. Okay, so this is in a very simplistic assumption, or very simplistic, not assumption, very simplistic form of the methodology by which we do machine learning, or what are the ways the machine learning works in the case of computer vision problems in general. And if you look into the computer vision applications, as I told, I will not read out all of this. These are very interesting problems, and there are many more, but these are the most well addressed problems which we find in the various references, right? Be it scene recognition, be it object tracking, be it human action recognition, pose estimation. Okay, it may be identifying a particular busy scene. And a lot of activities in terms of agent collaboration, in terms of the virtual reality for training the humans, in terms of analyzing the aerial images captured by your aerial vehicles, right? So these are all very good problems of computer vision, and a lot of researchers are there. The students can get interested to the latest research of any of these application areas, and many more are there. And this is just try to attract you all in the domain of computer vision. And what I also want to say is that you can understand that these problems are not so easy problems, and so obviously we will see that machine vision or machine learning, applied for computer vision, can give you a good good number of strategies to solve these problems. So this is a very typical example, which is taken from this particular website. You see that it is labeling. It is actually a classifier which is running at the runtime, and it is classifying each objects in the particular scene in a very accurately, right? You see the persons are identified as persons, a car is identified as a car, okay, traffic light is identified as a traffic light. So this is the outcome of a computer vision algorithm which runs well. Okay, right? And this helps in a lot of activities. Okay, it can be a navigation, it can be a surveillance, and a lot of others. Okay, so as I already uttered the term for supervised learning and unsupervised learning, you know what is supervised learning. In the case of supervised learning, we have a training data set or a supervisor. Supervisor means an already existing knowledge which helps, okay, which helps to develop your system. So supervisor is your teacher, right? Who handles you and try to put you into the try to help you in the learning path, right? And that's what supervised learning is. So supervised learning means you already have a good amount of knowledge, okay, which is already very well labeled, that you know that, okay, these are the items which forms class 1, these are the items which forms class 2, and these are the items which class 3, right? And then you look into the item and build your model. Look into the item means that you train your model with this particular different class levels, and there are various techniques that support vector machines, neural network, decision trees, Bayesian classifiers, okay, and many more, which works pretty well in the domain of supervised learning. The other way of learning is unsupervised, where the data what you see the knowledge what you have is not labeled, right? So you have the different types of data item, but nobody has told you that hey, this data item is it can be labeled as 1, or this class 1, this can be of class 2. So what you try to do, you try to find whether this object can be associated or this object can be deassociated, which means that you try to generate a feature measure, right? You try to generate a feature measure, and based on the measure in the feature space, you try to find whether the two objects are close to one another or the two objects are very far apart, right? If the two objects are close to one another, they can tell that they form a same cluster, or they are the part of the same cluster. If the two objects are far apart in the feature space, it means that these two objects are not of the same cluster, right? And this way you try to go on grouping the objects which are similar, and go on putting the objects in different groups which are dissimilar. And in this process, you actually form clusters, and clusters means that each clusters have the same type of objects, right? And then once you form the clusters out of your data, you can next you can just label the clusters, and then you can then you can use this for training once again, or you have solved your problem of clustering. Okay, so this is what is being done in the case of unsupervised learning, and there are several clustering techniques which are available to do that. So now I come to the other portions. That means other aspect of this, whether you are doing classification or whether you are doing clustering on your data. What you need to do, you need to work in the feature space, right? And then when you try to work in the feature space, that means an image. Okay, though it has a, that means though by seeing an image we are very happy. Many of the times it gives us a very good visual perception. But image in general is a complex representation, right? Because you can have different different scales of information in an image, right? So the fundamental way the image information or the image features can be abstracted are the pixel level features. Pixel level features are spatial features, right? And which can be either based on some spatial assumptions or based on some neighborhood assumptions. You can do that, right? Or some sort of sampling technique is used to understand the pixel values, or to get into the pixel values. Pixel values means that they're nothing but the intensity values. The other forms of features are transform domain features, right? So you take the pixel as your start point, but you try to convert the pixel. You try to apply some transform on the basic pixel information and try to go to the another information plane, like the edge distribution. So edge distribution works on the derivative of the pixel information. So derivative of the pixel information, if you try to do a discrete discrete gradient. You try to find the gradient in a particular in the image domain, which is a transformation. Okay, using a particular kernel. Okay, then you try to get what are the edge information, and then on the basis of the edge informations can work as a particular feature for your image, right? And there are different types of distributions you can analyze. You can go for the histogram distributions and all this transform domain information of the image. You can also try to form the feature vectors out of those. So this again depends on the problem. That means what is the exact problem, and whether it is fine for you to find enough features in the pixel domain itself, or it is not very convenient for you, or it is not very that means you don't get enough features in the pixel domain, so you try to do it in the transform domain, okay, in the frequency domain or some other transform domain, right? And that's why you know that this wavelet, Fourier, and all this comes into existence when you try to abstract the features in the transform domain. And these are the common tasks. I'm not reading it. You can just go into the classification, detection, recognition, okay, maybe categorization, okay, and maybe sequencing. So sequencing means that which objects are coming after that. So you can build a story, and that is mostly done in the case of video. So in the video annotation, you can have a sequence recognition or sequence classification, and you can try to generate the story out of that. Okay. So I'm not going into details. So these are the type of machine learning problems in computer vision: classification, regression, association, and clustering. So just a simple way I will try to go through. So classification means you can take an image and you can tell that, hey, this is a dog, this is a cat, this is a cow. Regression means you are trying to predict some value for the image, right? You are trying to associate a numerical value. So can you tell that whether the two objects are close to each other, or the two objects in the image are far to each other? So you can generate a sort of regression model which will try to predict that whether the two objects are pretty close, or whether the two objects are pretty far apart, right? And obviously you can be association or clustering, which is okay, in case of looking the object, whether you can to understand a particular scene. So when you find that, okay, there is a car, there is a road, and there's a traffic light, you will tell that, okay, I can associate these objects, and I can tell that this is a traffic, this is a busy road of a city, right? If you find a color of the sea, if you find a person, and if you find the sand beach, you can tell that, hey, this is an image of a beach. So these are the ways that means you can work on different types of motivation of applying the machine learning problems to solve the computer vision tasks. Now I am just trying to get involved from the classical machine learning approach, or the baseline machine learning approach. I'm trying to motivate you towards a neural network type of approach, okay, of machine learning, and then towards the computer vision. So neural network, I think many of you know this, and this is a very fascinating domain of information processing, right? And this is exactly the way our biological processing works, right? Our biological processing is basically done to the neurons. Okay, it's not a single neuron. It's a stack of neurons. It may be millions of neurons, which actually works in a different nervous system, right? And try to build this build a processing engine which is very strong. And obviously it takes a lot of things into consideration. It works with the memory. It works with some sort of a generalization rule. It can recognize patterns, okay, and it can also generate very useful decisions, right? These are the new real neural networks, right? To find the quality of these neural networks, right, of the biological, you can tell that means within a huge amount of noise also, right? Our neural networks, or our brain, or our neural networks which are there in the biological world can still understand what is the information that means, though it is very heavily infested with noise. For example, that means I think all of you know who is the person. But just I want to tell that, see, there is an immense amount of noise has been introduced in the image, still due to our recognition system, our strong recognition system, all of us, I think, understand what that means, whose image is this, right? And that's so important that some way we can cancel out our biological neurons can cancel out the noise and can understand what are the important information hidden in the particular image, and can generate that. So in order to generate this type of activity to your artificial systems or artificial computer vision, okay, your machine vision systems, it's a pretty challenge, right? It's a pretty challenge that whether we can really build this type of activities in our artificial neurons, right? And that's the way, and that's the motivation why people started working on neural network, right? The people thought that if we can build a network which can imitate the neuron activities which happens in the biological world, right? Uh, it can solve many of the complex tasks, right? And that's what the motivation. So to understand and this neural network is a pretty fundamental concept what you need to go along for deep networks, right? So many of the students I have found in my last 5, 6, 8 years of interaction with the students in various level, undergraduate, postgraduates, and PhD level, I found that many of the students doesn't actually take the concept from the neural network to the deep network. Rather, they try to find it is a different story at all, a different story altogether. Neural network is a different story. Again, a deep network is a different story. What I try to tell you is that, okay, maybe the architecture is that means pretty different, okay, in a deep network compared to a classical neural network. But the basic processes which are done in a neural network, right, are being done in the same way in a deep network. Only the processes are done in a little bit like a more connected way, and it does in a more hierarchical way. Okay, I will try to explain what I mean to say, right? So let's try to understand. So what I push here is that let us try to understand the basic neuron, okay, how it works, so that it helps all of us to understand how the deep network works. So this understanding is something that means a neuron, okay, which is called a perceptron. A very basic model of an artificial neural network is a perceptron model, right? And what the perceptron model gives you, the perceptron model tells you that it's pretty simple. It's pretty simple. It means that it has some input neurons, okay, which I have marked from x1 to xm, right? I have marked a neuron specially with a value 1. Okay, I will come to that why it is like that. And the other thing is that each of the input neurons are associated with weights, right? And which are being again numbered to W0 to Wm depending on the number of inputs. And what I then do, I multiply the weights with the inputs. Okay, so I do this xi multiplied by wi, and I do a cumulative sum of all of this over all the inputs. So that's why I equals to 1 to m. And then there is something called W0, which is also a weight which is coming here, but I have done it in a separate way, and that's why it is called a bias. Why I have done that? See, this bias is the parameter of the model, right? This bias is not the parameter of the input. So I try to make this neuron a very that means what I can say a very generic. So I strategically I put here 1, so that whatever W0 I put in my model, that will come as an additive factor with this and can be taken as bias. So just to make you understand it very simply, these are the actual inputs of your neuron, and this is an input which is from the model. So when you place the model, you tell what is my bias in the model. So you place the value of W0, which doesn't come from the input, but it comes from the bias. But as this input is being given 1, so whatever bias you give here, that will be additive with this particular part. So all this goes into this summation cumulative stuff, and this cumulative part is actually goes into the next layer, which is the nonlinear activation function. So this nonlinear activation function works here, and this generates the ultimate outcome. This is called an activation function because it actually generates an outcome, right? What outcome it generates? It generates an outcome by which we can tell that whether the neuron is activated or not. So which means that this activation function works on the input multiplied by the weights and the bias, and then takes a decision that whether the outcome will be activated or the outcome will not be activated. And this decision is based on this particular input which is being fed to the activation function. So the activation function is also called a decision function, which tells that whether the value of y will shoot up or whether the value of y will be marginal, right? Which may be very close to zero, right? If it shoots up, it means that the neuron is activated, right? If its value is marginal, it means the neuron is not activated, right? And that's the sole purpose of the activation function, to analyze the input, to give a decision for each of the neurons based on the input what is supplied to the neurons, and take a decision that whether this neuron will contribute in your decision as it is activated or will not contribute in the decision as it is not activated. So this is a sort of switching function, a nonlinear function, which actually works in the case prior to the outcome. Now, if you look into this activation functions, very simply there are many, but most commonly the functions are sigmoid or hyperbolic tangent or rectified linear unit. Okay, so what does function do, right? If you just look into the sigmoid function, you can very easily understand what it does. What it does any value less than 0. Okay, maybe just minus 0.2. Okay, it will squash it to 0. It will close to 0. I will take close to 0 because it is just to cross 0 in the negative side. Your value will subside to 0.2, right? And it will very close to 0. Now, just to go a bit high from 0, it will be something like 0.8, and slowly it goes to 1. So what this sigmoid function does, sigmoid function actually pushes any outcome which is greater than 0 to a high value, okay, close to 1, and any function which is any outcome which is below 0, which is negative, will push it to close to 0. So it means that if the combination, cumulative combination of the inputs and the weights with the bias, okay, is less than 0, the outcome, the neuron will not be fired. If it is above 0, the neuron will be fired. The tan hyperbolic function, which is called the tan H function, is also very similar to that. Only the difference is that instead of 0, it switches between -1 to +1. So if the value is low, it will push it to -1. If the value is higher than 0, it will push it to +1. The very interesting activation function is a ReLU, right? Why we need to know that is that because this ReLU function is a predominantly used as the baseline activation function for the case of the deep networks. Now what is that means how this ReLU is different from those of the sigmoid and hyperbolic tangent, we can just understand by looking into this particular graph. What this graph tells, this graph is something like max between 0 and z. So it means that if any input is less than 0, right, it will push it to 0 because between negative and 0, the max is always 0. So if something is negative, it will push it to 0. If something is positive, right, if there is some value of z which is positive, it will take the same value. So for all the z's which are greater than 0, okay, it will be the z. And if you look into these functions, right, it will tell that all these are nonlinear functions, because a function is nonlinear when its slope varies, right? So you see that all these functions, their slope varies, right, at different intervals of the function. So it's a nonlinear function. In the case of ReLU also, okay, this is a very important question one of my students asked me some time ago, that sir, a ReLU is a piecewise linear function, because if you see in this portion of the function it's linear, if you see this portion of the function it's linear, but still it is non-linear because it still has one change in the slope, right? It changes the slope from here to here, right? From 0 to 1, right? At a particular instance, and that's why ReLU is also a nonlinear function because it has more than one slope. Now the next question comes, right? Why ReLU is preferred, or why ReLU is becoming so important? ReLU is becoming so important due to one specific reason, that ReLU doesn't saturate. Now the question is saturates because you see that both these functions saturates. Okay, that means it becomes close to 1, and then you cannot have anything. Okay, you have only the same value goes on. Whereas in the case of ReLU, the value increases as we go on, increasing the particular value of Z. So it doesn't saturate. Now how it helps? It helps in the case that when you are trying to adjust these networks, right? You try to find what is the effect of your input, or what is the effect of your weight rather on your network outcome, right? And that's called the gradient analysis or backpropagation. What happens in this case of if the function is saturated, what it means that provided you give the input this, or maybe it is 4, whether you give the input 4 or 5 or 6 or 7, right? Your outcome is 1. So you don't get any difference or any appreciable difference in your outcome. uh, okay, when you change your weights, and that gives a change in your input to your activation function. So change in your input to an activation function doesn't show any difference provided within a certain range, right? Which means that your gradient, you cannot find the influence of your input on the particular outcome, and that actually called a vanishing gradient problem. In the case of ReLU, that never happens, right? Whatever input you give, your outcome will have a difference, okay, between the corresponding inputs, because it is a sort of ramp function. It doesn't saturate. So this is why ReLU is so important and so well used in the case of deep network to define the activation functions of the neurons. Now from the ReLU, there is also a particular way, as the ReLU is fine for the positive half, but if it goes to 0, the ReLU doesn't have any gradient. So to handle that problem, a leaky ReLU is also proposed, and in the case of leaky ReLU, the gradient is pretty small in the case of negative half, only just to stay the gradient, and just to understand that there is a difference between the negative inputs also in the particular activation. This leaky ReLU is actually being proposed, right? And last but not the least, there is something called softmax function, which is something giving a probability value to the outcome based on the input, right? And this is very well used in the classification in our deep networks at the classifier stage of the networks. Okay, so these are pretty common activation functions which are also used in the various levels of deep networks. And once from the single perceptron, single neuron, okay, you can migrate to what is called a standard neural network, right? In a case of standard neural network, you can tell there is one input layer, okay, there is a hidden layer, and there is a one output layer. Okay, this is a simple neural network. So the understanding is same. So what it means that each of the Z which work as a neuron will again collect the data from all the corresponding inputs which are connected to it, and the corresponding weights and the corresponding biases. So you see that each of the Z, which is represented as Zi, will nothing but the cumulative of the weights and the inputs for that particular J, for that particular I, okay, and there will be a weight for that particular I. So each of the ZIs will have their own weights for each of the inputs and their biases, which will be cumulative and which will generate the values which are coming at the Z1, Z2, Z2, Z4. Now when it goes to the outcome, these will be again similar. So these Zs will be nothing but now the input neurons, for your outcome, and then they will be passed through the activation layer. So each outcome Y will be nothing but a cumulative sum of all the Zs multiplied by the corresponding weights and multiplied by the bias in this particular layer, and then it will go to the activation function, and the activation function will decide whether this Y1 will fire or not, or whether Y2 will fire or not. So it's a pretty simple way from the single neural network, from the single neuron, you can go to building a neural network, right? So I will just keep a stop here just to check that whether if we have any questions. Okay. So I can have a couple of questions, okay, and then I will switch on to the last part of my lecture. So, so if you have any question, okay, I can take a couple of questions here.
It seems, sir, that there is none at this point in the chat.
Okay.
So if
Okay, fine,
one
fine.
has it,
Then I can
that's
continue.
yeah.
Okay, then I can continue to my presentations. Fine, perfect. Okay. So now I go to the deep network. Okay, after giving you the initial introduction, the concepts of neural network. So deep network. The fundamentals of deep network is basically called that one of the fundamental architectures, or the way the deep network started actually in the domain of computer vision rather. That means actually in the domain of deep network rather. Okay, it's a called a convolutional neural network, right? And you see there are two terms which are associated. Okay, one is called convolution, and another one is called neural network. So why it is convolutional neural network, why the term is something like that, it will be pretty clear for us, for all of us. So it is the same neural network. Okay, only we do, that means the weight transformation, what we try to do, the weight combination of the weights with the neuron, what we see in a conventional neural network is just being defined as a convolution operation in this convolutional neural network, right? And that's why it's called a convolution neural network. And this convolution neural network works for different types of data patterns, right? It can work on the data pattern which is one dimensional and a time series data, and if you are looking for the image data, it's a two-dimensional data, okay, of your x and y coordinates, and we'll try to see that how this CNN works on the image data. So just look into this model. So what we have actually understood in the neural network is that in the neural network there will be some weights for the neurons, weight associated with each of the neurons, and the weights will be multiplied with the neurons, with the values which are there as the neurons, as the input neurons, and then this combination, this cumulative combination, will go to the activation layer and will define the outcome. So similarly, this particular entire scenario can be defined as a matrix operation, right? So you see that. So what you try to give, you try to give y w0 x0 w1 x1, and b is the bias, which will be positive or negative according to your convention. You can take that, right? And this goes to activation function sigma, and then generates the outcome y. So you see that. The entire operation what we generate for y0, y1, y2, y3, y4, okay, everything, you can just try to expand this in terms of this linear combinations of weights and your input and obviously your biases, right? And so, okay, and so what we try to do, we try to expand it in a little bit better way. So when you have y0 and y1, two inputs, you try to give y0 w00 w01 w02 for the 0th outcome of the, and w10 w11 w12 for the y1. So in this way you can build up equations for all the y's, and ultimately what you can do, you can actually generate a weight vector, right, which is w0 w1 00, then w0 w1. So this way it tries to go, and this weight vector operates, this weight matrix operate on the x vector. Now the issue if it is an image, instead of x only having a linear dimension, in the case of image, x will also have a okay, that means okay, x will be two-dimensional. So in the case of the image, the neurons will be a two-dimensional input instead of a single-dimensional input, which has been shown here. So that what makes an operation of a set of image neurons with a particular matrix, and this operation is called a convolution operation, right? And this convolution operation plays a predominant role in the deployment or development of the CNN network, right? And let's try to now understand a very basic application of CNN with a very toy example. So the toy example here tells that, hey, using the CNN, can we try to differentiate, or can you try to understand what is the pattern X and what is the pattern O, right? It can look to us a very simple problem if the patterns are like this, X and O, right? If it's simple like this, I can just generate a particular template for X and O, and I can find whether the template matches with the input. If it matches with the input X, and it matches with the input O, I can tell if it is an X or it is an O. But the task is not so simple. The task is not so simple if we try to make a problem a little bit tricky. So what I do, instead of making the X, I can have several ways the X can be represented. So in our eye, which does actually neural computing, okay, that means we can tell very easily that all these are X, and similarly we can tell all these are O. But in a computer vision problem, okay, this pattern X and this pattern X are not similar straight away. Because what I'm trying to do, we're trying to take the pattern as a single feature, okay, and there our computer vision recognition fails. Okay, it fails here, right? Why it fails? Because what I try to show here is that I try to show that all the black pixels as -1 and all the white pixels as +1, right? And when we try to compare this and this image, you will find that the pixel information varies very much. Wherever I found red, the pixel information of the two images vary, and you see there are more number of reds here. So which means that these two images are dissimilar in their data content, and so your computer in a naive approach will tell that these two are dissimilar. Now, what the computer missed? The computer missed that no, it is not that means the pattern what we see. This pattern also have some sub patterns. So instead of trying to see the entire pattern as a single feature, if you would have searched some spatial smaller features in this particular image, in these two images, and try to compare on that feature space, probably you could have tell that this is also X and this is also X. How it happens? This happens in this way. So the features what we try to extract are something like this, and this, which means that it's a diagonal white, it's a white in the corner and white in the center, and it is the off diagonal white. So you see that if there was any way to abstract these features from both of these images, and then try to compare that whether these features and these features are similar in both of these images, you would have found out that yeah, indeed, these two images have the similar features, and so these two images are same. So what is the interesting point I want to tell you here is that, so there are a lot of features which are there deeply embedded in the images, and these features helps you to understand what the information is or what the image is. And without searching these deep features, okay, you cannot actually develop an algorithm which will be good for object identification or object recognition. Okay, so how you try to extract these features? To extract these features, you have to work on the feature kernels. So you see that I develop these three feature kernels, and these feature kernels are basically trying to work over the feature space, over the image space in a patch-wise manner. Okay, and we try to find that in which particular patches of the image these particular features are maximized. And then what we can correlate this with your weight vector what we have in the normal neuron. So this particular matrices are nothing but the weights which gets combined with your image data, which are spatially connected neurons, right? And in a 2D space, and then the weights multiplied by the values in the input neurons will give you a decision that whether these neurons are activated for a particular feature or not, right? And that is the entire game of your convolutional neural network. So what I try to do, I try to convolve this particular filter, that means over the entire image in a particular patch wise, and I take a sort of, that means a way I do a stride. A stride means how I move this particular kernel over the entire image area. So maybe I can start from here, and then I move to the move to the position which already being marked, and then I again move a bit in move one bit one column in the right, and this way we try to cover. That means we try to estimate the filter operation on all the that means all the patches, okay, for the particular kernel, right? And this we do for all the kernels, right? This we do for all the kernels. Okay, and what we generate, what we ultimately, so this is a simple way how we do the weight multiplied by the input neuron. So here we take that these are the weight vector which is defined by the kernel, and this is the input neurons which is defined by the image patch, right? And we do a sort of weight multiplied by the value, okay, and we try to evaluate this, and we try to do the complete convolution operation. By the process we do the complete convolution operation, okay, of this kernel over the image patch, right? And we do a sort of averaging of the value, and we try to put that particular value in my result matrix as one, right? And this way we try to do it, okay, we try to run this particular kernel in all the regions of the image and try to generate a complete matrix, which is a convolution outcome of this particular filter on the entire image in a patch wise. So these results are basically for the different patches where the kernel has convolved with the image, okay? And the size of the convolution is being defined by this particular convolution outcome, defined by this particular formula, where C is the size of the convolution outcome, okay, and that we can estimate by incorporating the size of the input image, which is here 9 cross 9. Okay, that means I will put 9 here in the case of I, and the input for the case of the kernel, it's a 3, so it's 9 minus 3, right? I didn't use any padding. So padding means if I would have added an extra layer, okay, in the boundary of this image, and that I would have given the same value as that of the last layer. So I put a layer which having all -1 values as is given in the last layer, and that if I would have done, it means I have done a padding. Okay, but in this case, as I didn't do any padding, I have a p value is 0. And this s is a stride length, which means that how I move this particular kernel over the particular image. So if I move by one position in the right and down in my each subsequent move, first I do the right and then I move down, then it's called the stride length is 1. So how I operate the convolution, that's the stride. So for this example, the stride is 1. So it means that what I'm doing, I am having a 9 minus 3 plus 0 divided by 1 plus 1. So it becomes 6 plus 1, which is 7, and this is exactly a 7 cross 7 matrix. If I wanted to keep this as again a 9 cross 9 matrix, as that was in this particular dimension, I would have just made a padding layer. So if I make a padding layer, you will find what happens. It becomes 6 plus 2, right? Padding becomes 1. So 6 plus 2 plus 1, so it becomes 9. So the outcome would have been 9 cross 9 layer. So that's the way we can estimate, because convolution in generally decreases the size of your matrix, okay? And so for 3 convolution layers, I have 3 convolution outcomes, right? And this is the way. And then what it comes the pooling operation, right? And the pooling operation is something that we try to after we do this operation, we try to take a window, and within the window I take the maximum value, right? And that we pass on. This helps in two ways. One way is that it tries to compact the feature space more, because wherever I found 1 for the particular kernel, okay, this will be now represented, okay, in a smaller dimension of the matrix, which means I've compressed the feature space. And secondly, what I've done, if this 1 has occurred here or here or here, okay, it would have been still be 1 here. So which means that if there is a little bit translational effect on the image pattern, this pooling will not be influenced by that. So this is the purpose of the pooling layer, and this pooling layer will generate all these things, right? And as we had three convolution outcomes, we will have 3 pooling layers coming up, right? In some cases, obviously, we can also introduce the ReLU layer, okay, which is the normalization layer in between. After we do the convolution, we can pass it to the ReLU, and then we can go the subsampling or the pooling. So ReLU, as we know, it will just suppress all the negative with 0, and it will take and keep all the positive. So what it does, ReLU actually tries to identify that which neurons are firing, which neurons are not, so that when you pass on to the max layer, it actually appropriately okay, takes only those values of the neurons which have generated a very high value. So in this way, this is the structure we try to do convolutional ReLU pooling, and this is the way we try to build the network. Okay, one after this is a hierarchical structure. So the first convolution outcome can give you some low-level features, and then you work on the low-level features. Okay, you try to work the concatenation of low-level features and go to the next high-level features, and then we go on like that, and we try to abstract the more high-level features out of your image. And what it ultimately last comes out is a fully flattened layer, which actually, that means I flatten the last. That means all the outcomes in the different channels. So these are actually identified as channels. So this is one channel, this is two channels, this is three channels, because I have used three convolution networks, three convolution filters. Sorry, three convolution filters. In a conventional networks, you will find there are 32, there are 56, there are 64, 128. This number of filters are there, and so you have those number of channels in your convolution network. Okay, and so based on a number of channels, you flatten the particular stuff, and you get a flattened network. And this flattened network will actually help you to classify. Okay, depending on the scores of the different neurons. These are actually now neurons, right? Flattened neural layer. So these are the neurons. Different. So depending on the different neurons, okay, you assign the whether it is X or whether it is O. So when you define this neural network, neural layer, okay, that means you have to assign some weights, okay, and these weights will be sufficient to identify if the weights of this and this are high, then okay, that means that this will identify whether it's an X, okay, and the weights of the others will identify whether it is a O. So when you try to put it as an X, it will give, okay, for the X class, it will have a more okay, that means it will adjust the weights in such a way so that the class X has a higher probability for these inputs, okay, and class O has a higher probability for these inputs, right? And this you can go on with a very standard neural network. So you see the probability value differentiates for a case of X and O, right? And this is what is being done in the case of softmax, as we told. So in the case of softmax, when you have trained, you have got the vector of x as this, and when you are passed as a test input, okay, you get the value of this flattened network as this, and then we try to estimate whether that means this particular input is a good outcome in response to X. Yeah, it gives a good outcome. It gives an outcome of 0.91, and whether it is a good response in terms of O. No, it is not a good response in terms of O, because it gives the probability of 0.51. So these are the ways you can assign the probabilities, and based on that you can detect a pattern, which is being done basically at the classifier level after the feature extractions. So feature extractions settles the value of the neurons which are being flattened, and then the neuron values are being evaluated based on a particular probabilistic score, so that you can identify what pattern has been passed in the input. So this is the way how it actually does. As I told that this is an input, and then you see that this channel, this is a 28 cross 28 cross 1, because it's a grayscale image. In the case of RGB, you will have cross 3, because there will be 3 channels of red, green, and blue. And 28 cross 28 is the number of pixels, okay? And this can be reduced a bit, okay, by resizing before passing into the fast convolution layer. So you have 24 cross 24 multiplied by N1. So N1 means the number of filters you are using, right? And then by max pooling, you reduce it to half, and then it becomes 12 cross 12. You use the same number of channels, because the number of channels in the convolution layer will be converted to the same number of channels in the pooling layer. But in the next layer of convolution, you can increase, you can vary the number of filters. So from N1 number of filters, you go to N2 number of filters, right? And this way you go on and go on and go on, and ultimately you can generate a flattened network, and this flattened network will then be connected with a neural network with some weight vectors, okay, for classification, and that will ultimately give you the classifier outcome. in the case of in the case of pattern recognition, you can have that handwritten text, handwritten number recognition. You can have 0 to 9 classes, and so your classifier will have 0 to 9 classes. Okay, this is the way I can have. There are some dropouts we can also do. So when we do these neurons, that means normally when you adjust with the training data, okay, that means you can work very hard to fit the fit this network to the best to the training data, but that doesn't work out sometimes well, because if you fit your data very well with the training data, what happens is that when you actually pass the real test data, okay, that means as it is overfitted, means it has been very that means it has been very tightly mapped to the training data. For the test data, which may be a little bit different from the training data, your result can be of high error. And secondly, if you reduce the number of nodes, your training time is less. So sometimes in this particular deep networks, dropout is being practiced. So just to randomly drop some of the nodes, okay, just to help in generalization, okay, then keep some error in the network so that it works in generalization and also reduces the training time. Okay. So not going to the questions, I will just go to the last sections of this. So this is what we can do in the case of RGB space. So this is the RGB space. What you need to do. So in the case of RGB, instead of one channel, you have 3 channels, maybe the simply red, green, and blue, right? In the case of color image, and what you do, okay, instead of a single layer, it becomes a volume image, right? Which has a depth, number of channels, and width and height depending on the pixel resolution of each of this RGB. And what you do the same thing, okay, using the kernels. But what you try to do, you try to add the values what is coming, and then you put it into the convolution outcome. Okay, this is the simple chip. You can just okay, you see that same thing comes up, but when you try to put the values, it will be cumulative of the R channel, G channel, and B channel, which comes in the convolution outcome. Okay, and now we can tell that so how the convolution, what are the convolution parameters you have come up. The convolution parameters depends on the number of convolution filters. Okay, for an example, if you have 6 cross 6 cross 3, which means that your okay, that means your patch sizes, right? Your patch sizes are 6 cross 6, right? And it is a color image, so you have 3 channels. So your filter will be also 3 cross 3. That means filter is reduced dimension than the image patch. Okay, that is the image size. So it's 3 cross 3 filter, and also you have 3 channels because you have to do for that means the 3 that means okay, for each of the channel you have to do the convolution. So number of filters is 3 cross 3, right? And okay, and the number of parameters you need to tune. So each of the filter kernels will have their weights, right? So a 3 cross 3 kernel will have 9 weights, right? And this will be done on 3 channels. So it will be actually this. So one kernel will have 9 weights. So if we consider 3 kernels, because it will work on R, G, and B channels, so it will have 27 weights, right? And okay, right, and there will be a bias. Okay, there will be a bias for each filter, right? So there will be a bias for each filter. So there will be a bias that will become 28, right? And then you take that these kernels will be 10. There will be 10 convolution kernels. So it will be 28/10 280 parameters. Okay, I think I am pretty clear. So let us first consider one kernel. One kernel will be of size 3 cross 3. And this will be operated on all the channels, as we have 3 channel image RGB. So there will be 27 weight vectors plus a bias vector. So 28 for one channel. And if I have 28 for one filter. Now, if we have 10 convolution filters, okay, like in our toy example, we have 3 convolution filters. Instead of that, if you have 10 convolution filters with 280 parameters, and that is the number of parameters what we should come up, right? And you see that, then you could also ask me this, sir, whether neural network, that instead of doing the convolution, if I would have passed this entire image as a single neural network input, right, what it would have done. So if it is a single neural network input, okay, you had a 32 okay, 3 cross 3, right, and it is a fully connected, okay, so So you convert it into a 28 cross 28, okay, into 6. Okay, that means you have a 6 nodes. Okay, 6 nodes in the hidden layer. So you have a 28 cross 6 number of parameters you have, right? Vis-a-vis, if you just look into our convolution layer, right? What you try to do, you try to have a 5 cross 5 convolution filter. Okay, f equals to 5, so filter size is 5, so 5 plus 5 convolution filter, right? And you, okay, that means, and you have a 1 bias. So we have 5 plus 5 plus 1, and there are six filters, right? There are 6 filters. So here we had 20h cross 20h is the image size, and 6 are the number of, okay, the hidden layer. So the number of parameters were 14 million. But in this case, you have number of parameters as 156. Because why? Because the parameters of each kernel, okay, are same in particular one layer. So you don't have to iterate on the parameters of a particular kernel for all the image data. So fragmenting the image into patches and then applying the convolution actually saving your number of parameters what you have in the network, and that's the crux of how you handle the parameters in the convolution layer. Okay, so I think I will not go into much. So these are some example networks which you can try. And these are the full description of the networks, which are very convenient networks in our normal image processing algorithms and image processing stuff. And I will not go into details of this. There are just a couple of slides. This neural network, which is basically a static network across the time, can be converted into, that means this particular network model is there, which is a recurrent neural network, which actually works in a way which is something like across the time you can okay. So this ht is a particular outcome of a particular time instant t, and then in the next time instant, this is called a hidden state, and this parameter can be passed as an input in the next state, right? And this way a recurrent neural network works in a sequence of data. So this may be a TH sequence, and then TH sequence outcome gets TH sequence hidden state gets as an input for the T plus 1 plus, and this is the way the activation function, and this is the way the outcome actually generates. So this I'm not explaining a very details, but what I want to say you is that combination of recurrent neural network with the CNN are very helpful for detecting an image information at a full. So you see the convolution neural network takes the features, and this feature sequence is passed into a recurrent neural network, and from that the image captioning, which is a very good application, which comes up, right? And you see that you have a star, that then you detect the straw, and then straw is passed to the next sequence, and then you find straw and a hat, and then you can tell that, okay, this is what is there. So this is the way how the convolution layer, and then followed by a recurrent neural network. Okay, recurrent neural network, which actually traps the sequence of. So what it traps the sequence of the objects which has been identified by the CNN are passed to a recurrent neural network, and then the sequence is identified, and from the sequence you can identify the image scene, right? And this is the way how it is done. So this is the way how image captioning is done. You can first identify a cat, you can then identify a suitcase, and then you can annotate that it's a cat sitting on a suitcase and then you can identify a floor, so you can tell that cat sitting on a suitcase on the floor, right? And this is the way how the image captioning, a very good example of two networks which are working in a cohesive way to one is trying to understand the sequence of the objects, and another one is trying to classify the objects. So this is the way in tandem they work, and they do a very good example of image captioning. But it is not that everything works fine. This is the very good references you can find. This is a public domain information which is available, and this is also a data which shows that in some cases it fails, right? So I not go further. So I end up here due to limitation of time. I can go on into generative networks and encoders, but I think that that means one lecture is not sufficient to cover everything. So I end up here. I didn't include my slide. What are the research activities we are doing? due to that means I was just trying to give my slide a shape last night, so I couldn't include that. So just to tell you that what we are doing at our A.K. Chaudhuri School of Information Technology, University of Calcutta. Okay, we are doing on multiple projects funded by different agencies. Okay, our predominant our predominant domain is obviously on the computer aided diagnostics. Okay, which we are doing with multiple institutes like PLS hospitals, like NR Institute Bangalore. We are also doing with the Spine Research Center in Park Clinic. A lot of activities are there. We a lot of collaborations in national and international domain. Okay, apart from that, we work on video analytics very heavily. On video analytics, we are trying to recognize the human actions. We are trying to do sports analytics. We are trying to generate some algorithms which can come up with some automated annotations of the informations. We had a last year 2019. We had a paper on CVPR on our sports analytics, which that means I think all of you know CVPR is the top conference in computer vision. Okay, and we had a paper there. And then apart from computer vision, we are using the deep networks for different types of research. Like we are doing energy renewable energy analysis with a project with University of Colorado through a funding of US LISA funding. We have projects with DRDO where we are trying to work with the learning patterns in security. We are also having a project with the DST with one of our Japanese university. We are trying to work on the quantum computing and machine learning. So and we are working with a couple of industries. Okay, there are some of the senior people from industry who are doing PhD in our research group, and that is helping us a lot to understand some of the industrial problems. We have a data science lab in our department of School of IT. We have a computer-aided diagnostics lab in our Center of Excellence in Biomedical Engineering, which is a multidisciplinary Center of Excellence in Technology campus. And both the areas I am okay. Then I take one of the lead role there. So the students and the faculties who are interested to work in the machine learning at a large, and obviously computer vision, okay, are welcome to connect my lab, and that's all from my side. So if any questions, I'm fine to answer.
Yes, thank you, sir, for the informative session. So this is for the attendees. If you have any questions, please feel free to unmute yourself and ask away, or you can use the chat. We are monitoring the chat as we speak, so you can have the questions if you want. Can we wait for about 2 minutes for this, sir, if possible?
Yes, sure. We can wait. Sure.
It seems like right now there are no questions.
Okay.
Sir, may I take this time to just ask for some resources for the beginners in the crowd that they can start on?
Sure. Okay. So I think the best way to search is that means you can look into the Kaggle, right? And there are a lot of this image processing data are there. Okay, there, that means if you also go into the Google Colab platform, right, you will have a lot of these data sets which are already there, which are already pretty well kind of okay, that means you can you can use those in the Google Colab platform. Okay, basically this handwriting recognition okay, problem, which is a pretty predominant database which works there. And I think you can start with building up your own neural network at first, and then go to the CNN, and then you can once you're comfortable with CNN, you can go to RNN, GAN, and this. And I think the best platform is in Google Colab. There are a lot of helps that are available for all these networks. So So they have a particular a baseline model that obviously it is not that can be uh, that is good for all type of applications, but they have a baseline model, Google Colab, which you can search. You can tell that Google Colab CNN, right? You have your Google Drive. You can create a Google Colab folder in a Google Drive, and then you can try to work with example codes. More essentially, what I try to say is that okay, you can always work with a code which is available, because there is no point point in redesigning the wheel. But what you need to do, you need to understand, right? What code you are running, you need to understand that code. So I will tell that you try to understand what are the network, what is the way the network has been defined, what is the way the training has been done. It's pretty important. So when you do the training, there are two types of things you have to understand. One is called the batch, and one is called the epoch, right? And we know that after in a case of mini batch, the weights are adjusted after the training of the mini batch is done. So how you update the weight, how you take the learning rate of your network, right? Those are some of the parameters you have to go on modifying and try to understand how it affects your model. Okay, yeah, Coursera deep learning specialization is a good thing. There are a lot of courses which are there by Stanford. There are good lectures from MIT. Okay, which can help you to understand this concepts of CNN, RNN, generative adversarial network, and autoencoder. I think these four understanding, that means you should know. Okay, that means fundamentally what that means. Okay, how these networks work, you should know, not only in terms of some standard library, but you have to know how they work. Okay, so that's all from my end. Yeah,
I
there are some
thank you, sir.
questions I saw.
Yeah, I believe there was one more question
Yeah, yeah.
based on the dropout layers in CNN.
Okay,
So the question was,
right.
what is the basis of dropping the nodes in CNN?
Okay, so if you see the standard programs which are there, they actually use a dropout that up to 0.4. So 0.4 means 40% are dropout. So dropout are basically done random, right? And this is a random. So dropout means that you try to drop some nodes. So so how it works, that if you try to drop some nodes, then the nodes which are existing, okay, there needs to be very well performing, right? Because you have dropped out some node. This is basically done to actually introduce a sort of sort of what I can say, sort of flexibility in your network architecture. And this flexibility helps you to 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 make your network more generalized. That means if you try to fit every component as per your training data, okay, it might be very good for your training, right? And that's called the overfitting problem. uh, but it might not be very good for the test data, because test data will be a little bit different from your training data. So now to accommodate that extra space, dropout helps, right? And secondly, obviously, your training time reduces in a dropout. As you have less number of nodes, you have less number of weights, and if you have less number of weights, you have less number of the training time to adjust those weights. So it helps in generalization, it helps in this, but normally it's done randomly, and it gives a good result. So I have seen some of the examples. Okay, we have tried out. It works until, that means 0.4 is also being tried out in some of the examples. Yes.
Thank you. So that was about it. Thanks again, sir, for this informative session. You can get in contact with Dr. Chakrabarti
Sure.
on LinkedIn, I believe. Yeah.
Yes. LinkedIn or over mails is fine. Yeah.
He's also a very active member of communities like Facebook Developer Circle Kolkata and Society for Data Science. Uh,
Right.
yes.
Right.
I would now request our head of the department, Dr. Piali Chatterjee, to give the vote of thanks before we close the session. Dr. Chatterjee has been very supportive of this initiative of the students for forming GNX, reviving the Linux user group, and forming an open source community around it. So without further ado, ma'am, please.
Thank you, Vik. So, it is my privilege to have been asked to propose a vote of thanks for this webinar. And I, on behalf of my own, on behalf of GNX team, and on behalf of my college, Netaji Subhash Engineering College, extend a very hearty vote of thanks to our distinguished speaker, Professor Dr. Amlan Chakrabarti, for raising your important work and sharing your valuable knowledge on computer vision and deep networks with us. So from this session, we have been able to know the key features of the various popular deep networks strategies like convolutional neural network, recurrent neural network, generative networks, etc. And also we have seen how they are being applied in computer vision. So definitely the session was indeed very informative and definitely it will motivate the research community. Thank you, sir. And I would like to thank our respected director and principal, sir, for their immense support. Many thanks to the GNX organizing committee, student and faculty members for your untiring support and coordination. My hearty thanks to all participants for their active participation. Also, your interaction, interest has made this event very successful and lively. I'm thankful to Institution Innovation Council for being with us. So with these words, we have to end up the session. Thanks to all. And thank you, sir, once again. Have a nice
Thank you
day.
all. Thank you, Professor Piali. Thank you.
Thank you, sir.
Thank you, ma'am. Thank you, sir, for the kind words. Yeah, do follow us on our social media handles for the latest updates on our webinars and seminars. So before we close, I would like to thank our guest of this time, Dr. Amlan Chakrabarti, once again. Thank you, sir. He will also be a guest, I believe, at the first IEEE International Conference for Convergence in Engineering organized by our college, Netaji Subhash Engineering College. So you can catch him there if you have presented a paper or have registered for it. Thank you everyone for joining us. Hope
Thank you,
have
Ovi, for conducting this session in a great way. Thank you.
Thank you, sir. It's an honor, sir. I hope you will give us the honor of hosting you once again in a future webinar.
Sure.
Thank you, sir.